Hey dudes, Dude the Builder here, and in this episode of Zig Master, we are going to be taking a look at some Zig code that will try to prove what we just saw in the world of the concepts of memory and the process virtual address space. We're going to be bringing this into the practice world here, out of the theory. So let's get started here. The first thing that we're going to look at is our container level declarations. We have here a global constant of type F32 and a global var of type usize. And the first thing that we're going to be doing here in our main function is we're going to be doing a debug print of the addresses. What we're going to be using is this built-in here called int from pointer, which will convert a pointer to its numeric address as an integer, exactly as a usize. And we're using here the address of operator, which creates a pointer to a variable or a constant. In this case, here, the address of global const and the address of global var. Okay, that's simple enough. Let's go to the terminal and let's do a zig build run. And as you can see here, we have that the address of our global const, it begins here with 102.9b. Our global var is at 102.9c. Okay, so they're pretty close in this address space. Let's go back. Let's clear the screen. Go back to the code, and let's now create some heap allocations. Let's comment. Let's see up till here. And what we're going to be doing, we're going to be creating here an instance of our general purpose allocator. We'll be talking more about allocators further down in the series. There's also some videos about allocators in the Zig in Depth series. And although that series focuses on Zig 0.11, there are a lot of concepts that are still valid. Basically, once we have our allocator, what we're going to do, we're going to be using, as we saw in our previous video, we're going to be using the create method with just a U8 type. So we want to allocate a single byte on the heap, and we're assigning that to this constant called heap1. Here we use defer to call the destroy method because we want to clean up after once we're finished. Defer will execute this when the scope exits, which is basically when main exits here. And we do the same here with this constant heap2, once again using create to allocate on the heap. And then once again we are using here our debug print to print out those addresses using the int from pointer built-in. Okay, here we don't have to use the address of operator on heap 1 and heap 2 because heap 1 and heap 2 are already pointers. Okay, that's what's returned from the create and alloc methods of allocators. So let's save this and let's go back to our terminal. I'm going to be using my alias for Zig build run. And as you can see, we still have now with each run you will have different addresses. That's expected because there are different things running on the system and the addresses will change. But in terms of the general locations, once again it's pretty similar here. We have once again here the 100f for our const and 100f again for our var. And for our heap allocation, we have 1010, okay, and 1010. So as you can see, these two heap allocations are close together, but they are farther apart, and they are higher up. They have higher addresses in the address space compared to these container level declarations. So in fact, we can start seeing here that the container level, the constants and the global variables are in a close together region of memory, which would be that static block that we saw. And heap allocations are close together, higher up in the address space. Okay, so let's go back to the code. Now here I have this little utility function called printmem, which will help us out. We were going to be printing out a parameter, a constant, and a local variable. When it comes to our functions, we have here our first function called a, takes a parameter of type U8, and we are declaring within a local constant, LC, type U8 has value 42, a local variable has value 99. We print out a here so we know that we're calling a, and then we use our utility printmem to print out the addresses of the parameter, the local constant, and the local variable. Okay, so let's move on down here in main, and let's uncomment this line here. So we are calling that function a, and let's see the output. Here we go. We have the function a. The parameter is an address starting out at 16D, okay, ending up in 57. The constant is in the memory starts at 102, okay, and as you can see here, it's the same 102 here and 102 as the globals, okay. This time the heap also, we have 102 in the heap, but it is higher up because here we have 102.87. And here we have 102.8C. So there is a difference here, a gap between the globals and the heap. And here our constant, you could say that it is much closer, 102.89. We have 102.87 here, 102.89 also here. So this constant is definitely in this same static area, static block area. Where our container level constants and variables are, even though this constant is defined within the a function, as we discussed. And our variable, once again, we see that it's in this 160, starts out with this prefix 116. Another thing to note is that the parameter ends in 57 and the local variable ends in 56. So you would say that the local variable is coming first before the parameter, which would be a little strange because in the function definition, the parameter comes first. Well, the thing is that it is actually first because remember that the stack is growing downwards in the address space. So higher numbers in the stack come before lower numbers, okay? So the parameter indeed is first, and then we have the local variable in memory. And this is in the stack, and specifically in the function's stack frame, okay? So let's go back to the code, and let's uncomment this B function. Let's move over here, and let's take a look at this B function. Once again, it's basically an exact copy of the a function. We have the same type of parameter, declaring the same local constant with the same value, same local variable, the same value, printing out b, and using printmem to print out the addresses, okay? So let's save this, and let's run this. And here we go, we have the call to b, and as you can see, we have exactly the same address for the parameter, and we have exactly the same address for the local variable. And as a matter of fact, we have exactly the same address for the constant. But the constant is proof of what I said, that even though the constants are declared inside a variable, they are being placed in the static memory block region. And in this case, since we are storing the same value, well, the constant declared in a different function, it's pointing to exactly the same address, okay? So we have a deduplication there. We don't have to store the same value twice. It's never going to change, so we point to the same address. And this behavior of having the same exact address for the parameter and the local variable as in the a function This isn't an instance of deduplication. This is a result of how the stack is behaving precisely as a stack data structure. When we call B, we already returned from A. So A stack frame, which in this case was beginning at this address here, ending at 57, it's popped from the stack, it's removed, and then B can be placed in exactly that same spot. Okay, so B's stack frame begins at the same place, and since these two functions have the same data types for the parameters and the constants and the local variables, it's basically taking up exactly the same space in the stack. So B's stack frame is in exactly the same place and taking up the same space as A's stack frame. Okay, but it's not that they're pointing to a same separate address as is the case with the constant. It's that the local variables and parameters are being placed in the same spot in the stack because A has returned and its stack frame has been popped. Okay, so let's go back to the code. This time we're going to be taking a look at a little more complex example. Let's uncomment up to here. C, as you can see here, we have this function here, C. We're passing in the literal 15. But we now have that C returns something, and we are using this destructuring syntax. We're declaring two constants, pointer to const and pointer to var. And what this refers to is that C is going to be returning two pointers. One pointer is to that constant defined locally inside of C, and the other pointer is pointing to the local variable on the stack. So let's move up here to the definition of C. As you can see, we're receiving one parameter just like before, but now we're returning here. We have this anonymous struct literal definition here. First element of this is a pointer to a const U8, and the second one is just a pointer to a U8. Here we have our local constant, but this time it has a different value, 3 instead of 42. The local variable has the same value, 99. We're printing out here C to know that we're in C. Once again, we print out the addressing for the parameter, the constant, and the variable. But now, one thing we're also doing, we're going to be calling B from within C. So before C returns, we are making a call to B. And then once B returns, we can return from C, and we are returning the address of the local constant and the address of the local variable. Okay? So once we have that, we will be, once again, printing out the address of that pointer to the const inside of C that we received, and the pointer to the var inside of C, and the actual value. We're using here the dot asterisk operator to dereference the pointer that we received in both cases, so we can obtain the value that's being pointed to. And don't worry if you're not familiar with pointers. We'll be talking extensively about that in the series. But for now, let's just take a look at what we get from this output. Let's do our sig build run. Okay, now we have here our call to C, okay, in this line over here. And once again, as you can see, we have the exact same address as before for our parameter, and also for our local constant, for our local variable, sorry. And the constant is in the same address region as we can see here from the start, but the ending is different. Now we end in 6, while the other ones end in 5. And this is because this constant in C has a different value. So we can't point to that same value stored from A. We have to allocate another byte in the static area, and now we're pointing to that other address, okay? But the local variable and the parameter stay basically in that same place in the stack frame, in the stack, which begins at the same spot where A and B were beginning. But now, before C returns, we are calling B again. And now, as you can see, the address for the parameter of B is different, okay? Here we're ending in AD17, and here we're ending in ACD7. The same thing with the local variable. Here we're ending in AD16, and here we're ending in ACD6, okay? So this proves that the stack is indeed behaving as a stack, and it's growing downwards in the address space. This address ACD6, it's numerically comes before this address AD16, but since the stack grows downwards and higher addresses come before lower addresses, then this proves that in this case the stack frame for B comes after the stack frame for C, because C hasn't returned, okay? And that's why you can't place B in the same spot in the stack where C is, as we did previously, because C hasn't returned yet, okay? And here we have that our pointer to that constant within C, it ends in 6, as we see here, and the value is indeed 3. And the pointer to the local variable in C has this address here ending once again in D16, as we have here, D16, okay? The value is 99. So as you can see, we successfully returned a pointer to the constant and a pointer to a local variable. But you may have heard that returning a pointer to a variable within the stack isn't a good idea. And we're going to see why that is so. Let's clear the screen here. What we're going to be doing here next, let's uncomment this. As you can see, all I'm doing is we just, here we printed out those addresses and values. Well, I'm going to do the same thing again. I'm doing exactly the same debug print call with exactly the same parameters here, the same arguments. The addresses and the values. That's all I'm doing, okay? Let's go back here to our terminal, do a zig build run. And what do we have here at the end? Well, we have the constant with the same address, same value, no problem. We have the same address for the local variable, but the value has changed, okay? And we didn't mutate this value directly. So what happened? Well, if we go back to the code, you see that once we call here, we call the C, okay? And we obtained that pointer. And the next thing that we did was call this debug print function to print out the pointer address and the value. Well, this debug print is indeed another function. So its stack frame is going to be placed in the stack. And that's what happened. The stack frame for debug print overwrites whatever was in that area of the stack that was previously used by C's stack frame. And once this debug print is finished, that value was overwritten, and that's what we see in the next debug print, okay? That's why when we look at the output here, we see that now we have 0, and it could be basically anything. It all depends on the next function that you call. So this is why you shouldn't take pointers to memory in the stack, in the function stack frame, because once that stack frame, even though the first time here we still had the valid value of 99, you may think, hey, there's no problem. But once you call another function, you don't know what's going to be there. So this is what's sometimes also known as a dangling pointer. Okay, you're pointing to memory that you don't know what's going to be there because it's going to be modified or written to by some other part of your program. So that's why you shouldn't take pointers to memory on the stack. Okay. And with that, that's basically all I wanted to demonstrate here. These addresses basically demonstrate what we saw in theory in the previous video. The different areas are globals, are in the static area. Our heap allocated values are in another area higher up in the address space. And here we see the behavior of the stack behaving as a stack data structure, where you add, you push frames into the stack and you pop them as you go along. And finally, well, we see how we can take a pointer to a constant even though it's defined in the function stack frame, because it's not going to be stored in the function stack frame. It's going to have basically a static lifetime. But doing so with a local variable is a bad idea, okay? You're pointing to memory that once the function stack frame is popped is invalid, okay? So I hope you find this useful. Dude the Builder here. I'll see you in the next one.